So once again, I welcome all of you in this lecture. This is the differentiation of implicit functions related to my previous video number 4, and which is a remaining part of exercise 5.8. Now I would like to take question number 9, which already I have noted down. However, I will request you in books have different prints in different years, different editions. So the question number may vary by 1 or 2 number. Kindly don't mind, you can match. So here it is sec x plus y upon x minus y equals to a is a constant, and we have to find dy dx. We have to prove that even dy dx equals to y upon x. Then how to do this? If one go directly, then he has to apply the chain rule of differentiation. First he has to differentiate sec, then it will go inside, then the quotient rule will be applicable. Rather than doing by this way, what we do, we simplify this. X minus y is sec inverse a. Now sec inverse a being constant can be taken as k. So it is x plus y, x minus y equals to k. Now here we apply componendo and dividendo theorem. So it will be x plus y plus x minus y, x plus y equals to k plus 1 upon k minus 1. So here you see this y is cancelled and here x is cancelled, and once again it is k plus 1, k minus 1 is a constant. So it is 2x upon 2y equals to, suppose, a constant k dash. 2 get cancelled. So it is x upon y equals to k dash. Now we can differentiate with respect to x because we need dy dx. That means to find dy dx, we need to apply differential operator what? D dx. So we apply d dx over this quotient x upon y equals to k dash. What happens, see here? Here we have a quotient rule, y square, y differential of x with respect to x is 1, x differential of y with respect to x is dy dx equals to k dash being constant, differential is 0. Y square is cross multiplied to 0. So y minus x dy dx equals to 0. This implies that dy dx equals to y upon x. That is your answer. You can see once again entire solution if something is missing. You may pause and you can see this entire solution. Now once again we have this question from the same exercise 5.8, question number 10, first part, where y is equal to x sine a plus y, and we have to prove this. Now we can do in many ways, but before in questions of proof we should observe what we have to bring. So we have to bring the answer in terms of y. So what we do, we make x as a function of y, like y upon sine a plus y. And now we differentiate with respect to x because we need to find dy dx. To find dy dx, we need to apply differential operator d dx. Okay. So what happens here? Here differential of x with respect to x is 1. Here we have a quotient rule, sine square a plus y. Now remember, differential is taking place with respect to x, and here the terms of y are there. So denominator function and differential of y with respect to x is dy dx minus y. Differential of sine a plus y is cos a plus y, and then you go inside and becomes dy dx. Now this is cross multiplied here. Sine square a plus y equals to, we may take dy dx common here in the numerator, sine a plus y minus y cos a plus y. So finally dy dx will be sine square a plus y upon sine a plus y minus y cos e plus y. That was a proof. we have now this question from the exercise 5.8, that was 11th second part. Y equals to square root of sine x plus square root of sine x plus square root of sine x inside and continued for infinite terms. So what we do, since all this structure is like y, so from here we can summarize this as how y equals to sine x, because this is looking like y, so this place can be replaced by y. Now we can square on both sides. Now it becomes a implicit function because x and y are both mixed. We are not able to distinguish whether y is a function of x or x is a function of y. However, the requirement tells us we have to take whether y is a function of x or x is a function of y. For example, if dy dx, then we have to understand y is the function of x, and if somebody needs dx dy, then he has to take x as a function of y. Since we have to find dy dx, so we need to apply d dx operator over y square sine x plus y. That means 2y dy dx is cos x with dy dx. What is the meaning? Since y is taking place with respect to x, so here n term always dy dx. Here nothing as an end product, because both x, the differentiation of a function having variable x with respect to x, so it remains as clean without any dy dx term. Once again, here we are differentiating y with respect to x, so dy dx. Now later it is very simple. Dy dx is 2y minus 1 equals to cos x. So dy dx equals to cos x upon 2y minus 1. That is the answer of this. Now after this we come on the exercise. Now we are extending the idea beyond this particular exercise. Now I want to bring some other standard formulas like differential of e to the power x is, which already I have told you earlier, but I want to revise it. Differential of e power x is e power x. Differential of a to the power x is a to the power x into log a to the base e. And differential of ln x, that means log x to the base e, it is 1 upon x. And the differential of log x to some other base a is 1 upon x log a to the base e. These are the 4 formulas which we require for exercise number 5.10. Exercise 5.9 already we have done in class 11th. So exercise number 5.9 we have done in class 11th. So exercise 5.10 has a question based on these 4 formulas. So I'm taking few questions from this. Like we have third second part. Now here chain rule will be applicable with the help of new 4 these formulas. E to the power sine inverse x. We apply differential operator to find dy dx. So dy dx. Now you will reach here. So this sine inverse x. The sine inverse x is taken as an x. So e power x, but there is no x, there is sine inverse x. Then you will reach here. So sine inverse x, differential formula already we know, that is under root 1 minus x square. That is the answer of this question. Suppose next question we take 5, first part, y equals to log of log x. Remember, when base is not given, this is always taken as d dx of log x. So in the calculus, when base is not written, it is taken as natural log. So once again, d dx of y equals to log of log x. Now we differentiate by chain rule. dy dx. Now you reach here. So this is taken as an x. So it is 1 upon x. But this is taken as x. There is no x. There is what? Log x. Then you reach here. So log x differential is 1 upon x. Then in the end actually you reach here. But it differential is always 1. Differential is 1. Why? Because differential of x with respect to x. So that's usually we don't write. To convince you I have taken this step. Even we don't speak about this. So directly your answer is 1 upon x log x. Remember this is natural log. So next question from the same exercise 5.10, that is question number 6, second part. We have this question. Suppose we apply a differential operator over this tan inverse e power sin x. So by the chain rule of differentiation, see what happens. First you reach here. Alright. So this is taken as an x. This is taken as an x. So it is differential of tan inverse x 1 upon 1 plus x square e to the power sin x. Then you reach, starting we reach here e power sin x. So it is taken as e power x, e power sin x. In the end you reach sin x cos x. So that is a question through which you deal this. Now next question from the same exercise 5.10. I take this y equals to 2x tan inverse x. So dy dx is 2x, differential of tan inverse x is 1 plus x square, and plus tan inverse x, differential of x is 1. Now here the chain rule will be applicable. 1 upon 1 plus x square. Then you reach here. It is 0 plus 2x. So finally it is 2x upon 1 plus x square to tan inverse x minus 2x upon 1 plus x square. It get cancelled. So it is nothing but answer is 2 tan inverse x. Now next question from the same exercise of differentiation, the 12th first part. Why is this? So we differentiate dy dx. You know quotient rule will be applicable here. Now here denominator function, numerator function differential is 5 to the power x is log 5 and log x is as it is minus 5 to the power x log x. I'm sorry. Once again, to see the differential of this, see dy dx. Before this, I would like to tell you that differential of 5 to the power x is nothing but 5 to the power x is log 5 to the base e. So it is according to quotient rule x square plus 1 whole square, x square plus 1 differential of 5 to the power x log x minus 5 to the power x into log x and differential of x square plus 1. So remember x square plus 1 whole square. Here x square plus 1 as it is. Now we have to differentiate this because there are the two functions 5 to the power x and log x. So first we differentiate 5 power x as 5 power x log 5 and log x is as it is. Then we fix 5 power x, differential of log x is 1 upon x. Then we come here 5 to the power x into log x and differential of this function is 0. Later you have to simplify this. X square plus 1 5 to the power x log 5 into log x 5 to the power x upon x minus 5 to the power x log x whole upon x square plus 1 whole square. Now after this algebraic process is left in which you have to take 5 to the power x overall common and so on. That you can do, I'm sure. This another question I want to bring from exercise 5.10. This is a function y equals to log x under root x square plus 1 and whole divided by under root x square plus 1, and we have to prove this. Now it is looking as an explicit function because y is looking function of, or it is made from variable x only. But now we can make this implicit by multiplying x square plus 1y log x plus under root x square plus 1. Now we can differentiate this. We apply the differential operator. So first we differentiate this. 2 root x square plus 1 into 2x, y as it is, x square plus 1 into differential of y with respect to x is dy dx. On this side we apply the arrow method or chain rule of differentiation. Here you are striking over log, this is assumed as x, 1 upon x, but there is no x. There is no x, x under root x square plus 1. Then you reach here, that is 1 plus under root 2 under root x square plus 1 into 2x. 2 get cancelled. So it is 2 get cancelled, x upon under root x square plus 1, x square plus 1 with y under root x square plus 1 dy dx equals to 1 upon x under root x square plus 1 under root x square plus 1 plus x upon under root x square plus 1. It get cancelled. Now it is cross multiplied on this side. xy, this cross multiplied here. X square plus 1 dy dx equals to 1. Hence proved. So that was an introduction of exercise 5.10. I'm sure that you will be able to deal the question. Please take the help of the solved examples to solve the questions of this exercise. Thank you.